this lecture, we're going to study imperfect bifurcations. So far we have studied the pitchfork bifurcation, in which we had uh, a vector flow which looked something like this. Again, it had a very distinct symmetry where x and minus x, they are evolving as per the same function. Now, often in many questions there is something called as symmetry breaking, and a parameter which can break the symmetry of this equation is a simple constant term, something as simple as this. Okay, so given this prototype equation, there are now two control parameters. The first control parameter is h and the second control parameter is r. So upon changing these two, we can have various characteristics of the equation. So when h is equal to 0, we do reduce to a normal mode of a pitchfork bifurcation. So let us first look at how this function actually looks like. So let me copy this bit of code. We'll need all of this. Okay, so now let us define. So let us define fx as a function of x h r, and it will return h plus r times x minus x cubed. Let us wrap everything inside another function which will take inputs as h. Let me take the default value of 0.1, and r, which will take a default value of 0.5, for example. Let me put all this inside the function block. Okay, so now x equal to np dot linspace minus 3 to 3, 100 points, y equal to fx of x h r plt dot plot x comma y. Let me define an interactive widget. So w equal to interactive show imperfect, and we're gonna pass h equal to minus 2 to 2 in steps of 0.05, and r equal to minus 2 to 2 in steps of 0.05. Let us display the widget. Okay, so after running this, let me also draw the x-axis of plt.ax v line, h line 0. And let me make it something like this. Oops, sorry. Okay, let me change the y limit also, minus 0.5 to 0.5. Yeah. Okay, so now let us vary h. So when h is 0, we have two roots for r positive. Okay, so when r is positive and h equal to 0, or rather let me classify it as this. So h equal to 0, r is positive, two roots. When r is negative, okay, so there are no more two roots. So when r falls below 0, there's only one root. Okay, and this is a stable root. Okay, so this root is stable, meaning it's a stable fixed point. When r is greater than 0, what do we have? This is stable, this is unstable, this is stable. Oh, so there are three roots, not two roots. There are three roots, two stable and one unstable. And this is obvious, this is simple pitchfork bifurcation. Okay, when h greater than 0, there is only one root. For r greater than 0, only one root, and that is a stable root. When r less than 0, there's still only one root. When r actually is pretty large, there's presence of two roots. When r greater than some critical value, you have two roots. And sorry, not two roots, you have three roots. So depending on what value of r you have and the combination of h. But when h is negative, okay, again you can have a certain r at which again you have three roots. So r and h, they determine whether the equation has one root or the equation has three roots. Okay, and while it may not be entirely clear what is going on in this cubic equation, we can actually split this equation into two parts. Let me copy all of this. Let me paste it over here. We can actually break this equation into two functions. So when we are searching for a fixed point, obviously x dot will be equal to 0. So h plus rx minus x cube equal to 0. So we can plot two curves. So the first curve can be h plus rx, and the second curve can be x cube, and then we can look at the intersections of these two curves. Okay, let us actually try to plot this. So we don't need this. So actually let us create it from scratch, but let's not copy paste. Okay, so let us remove this. X equal to linspace, so y equal to x cube. All right, so let this be y1 and y2, let it be h plus rx, r times x. So let us plot simultaneously x comma y1, x comma y2 and the x-axis. Let us now wrap everything inside a function. H comma r. Let us put all of this inside the function. Let us remove this. Okay, so let us pass h and r. Show imp1. All right, so let us execute this. Okay, all right, so look, when r is negative, so okay, so right over here it is quite obvious that h is the intercept and r is the slope and x cube is x cube. Okay, so x cube is not gonna change. But what is gonna change is this particular line. So when r becomes positive and as h changes, we can have 3 points where they intersect. 1, 2, 3. Okay, so it is all about how we can rotate the line, slide it around. So we can have 3 intersections like this. If I change around h, we are having just, see, over here we have one point of intersection near -1 and another point of intersection just about to originate around something between 0 and 0 and zero point 0.2. So it's tangential, so that straight line, that is h plus rx, is now tangential to x cube. If I now increase h, now we have 3 points. Until this point, now we have only 2 points. So the lower branch of x cube is now tangential, and now we have only one root. Okay, so this is how we can sweep across the parameter space and find out the intersections. So in the case of imperfect bifurcations, the whole idea is one parameter is not solely guiding the nature of the equation. Rather, there are two params, and if we were to extend our discussion to something in the RH plane, okay, so there are various combinations of R and H where you have two roots, rather one root. There are certain combinations of RH where we have three roots. Okay, so now let us try to identify exactly what is the parameter space and how many roots do we have. Is there some demarcation, and can we find out how R and H dictate the nature of the equation in at least the number of fixed points. We will discuss about the stability of the fixed points later on, but at least let us look at how we can summarize the number of fixed points of this particular equation. So let us now write a snippet to find out the parameter space. Okay, so let us go to the previous lecture. We'll reuse this particular code. Okay, so parameter space of h comma r. All right, so we've pasted this, and so the function that we are worried about is this. So x comma r comma h, x comma r comma h, and this has to be h plus cubed. This will be r minus 3 times x square. So we don't need x anymore. So we need ra and ha, and we will need we'll be bothered with r on the x-axis and h. This will be np dot mesh grid ra and comma ha. All right, so for r in ra, for h in ha, or in fact this has to be in terms of I and j. For I equal to n, I in np dot a range 0 to np dot size of ra. For h in np dot a range 0 np dot size ha, this has to be j. Okay, so we missed a comma, we missed a bracket over here. Okay, so then r will be ra I and h will be ha of j. All right, now we must solve the equation. Okay, let me just indent everything. So now instead of using the fsolve solver, we'll now go to the Newton solver. Okay, so for using the, because fsolve solver is not really efficient for finding us all the roots. I know that in all the previous lectures we've been using the fsolve, but using the Newton will give you far better results. Try to rewrite all the other codes in terms of the Newton solver. You don't need to change everything, but just follow along. It should be rather simple to do. So here let us import from scipy dot integrate import Newton. Okay, let's some scipy dot optimize import Newton, and over here, so this has to be Newton, And the Newton syntax, uh, if I remember correctly, so f prime we have to supply, so this will be df dx. The initial guess, let me define it as xg, and we will define the guess range equal to np dot linspace -3 to 3. Let us take 5 points as the guess points, okay, in order to cover all the three roots. uh, args we have to pass r comma h, and full output will be equal to true. Okay, so we are worried about the number of roots, so we don't really bother about plotting it for now. All right, so we don't care about this. Let us get rid of this. Okay, so in fact, let me create a new cell to show you what the output structure of Newton looks like. Okay, let me paste this. Okay, let me pass r equal to 0.2 and h equal to 0.3. Positional, so this has to be x0 equal to, okay. We have not defined xg. Okay, so let me fix this as well. All right, so this has run. Let us probe what soul is. So soul contains these things. It contains a root, it contains converged, which is the array. So all the roots have converged, which is fine. And okay, so we are more bothered with soul 0, which is the root array, and soul 1, which says whether all the things have converged or not. Okay, I'm trying to show you this because from this we'll really get to know something. So let me change the value of r to something maybe 0. Minus 0.2. Okay, still all the roots have converged. Minus 0.2. Still all the roots have converged. Still everything has converged. Okay, so for this parametric set, we have two roots. Not two roots, we have three roots. One is this root, one is this root, and one is this root. And we necessarily give a large number of initial guess points so that even if there are multiple roots, we converge to those roots eventually. This has something to do with the Newton's basins of attraction. Okay, regardless of where we start, we are converging towards these roots. So now, suppose one of them would be false. Okay, so in case one of them were to be false, it means that that root, whatever it has returned, it is not actually a root which is truly returned. Okay, we have to discard that root. So then for extracting the true roots, so roots equal to sol 0, okay, whether converged equal to sol 1. Okay, so now these are the two things. So now roots which are converged will be roots of those indices which are true. Okay, whether converged. Okay, so now roots converged will contain those roots which have converged, but we want to find out the unique roots. So now we will say np dot round this comma, let's say 2 decimal places. And the reason I do this is if the numerical algorithm has some issue in converging, or if it converges to 10 to the power minus 8, so beyond that, I mean, although it's the same root in true mathematical sense, but the computer representation does not make it look like a same root. If you do a equal to b, it will say false because it is maybe different at the 10 to the power minus 12th place. Okay, so in order to avoid that, you can simply round it off to 3 decimal places. It will still appear correct. Okay, so now out of this we will extract the unique elements. So np.unique. So it has now given us only the set of unique roots. And so now let us print not only the roots which have converged, but also the number of roots. So then np.size of roots conf. Excellent. So now we have all the things. So this is the code that we are more interested in. So we'll copy this. Okay, we'll go over here. So then for once we have the solution, we will copy paste this thing. So roots will be sol 0, whether converged will be sol 1, roots converged will be this, and number of roots will be np.size roots converged. And lastly, we will assign everything to an array c j comma I equal to number roots. And here we will define c equal to np dot zeros, np dot shape of r. So this is just an initialization of the c array with zeros. So now np is the number of roots. Yeah, that's pretty much it. plt dot p color c, or rather r comma h comma c. Aspect ratio 1. We don't need the limit. We don't need the x line y line. X level is x and y level is h. plt dot color bar, and the title of the plot will be bifurcation, or the stability diagram. It is often called as the stability diagram because it shows in the parameter space how many fixed points a given state has. So let us run this. Okay, so obviously there was some warning, but we ignore that warning for now. Maybe it started with this point where it is not able to converge. In fact, let us refine the grid. So we see that something is happening over here. So let us define the grid from minus 0.5 to 2 and minus 1.5 to 1.5. Minus 0.5 to 2 and minus 1.5 to 1.5. Let me run this. So let me refine the grid. Let me take 100 points. Let me run this, and after a while we get this diagram. So inside this there are 3 roots. Over here there are 1 root, and this is the boundary which separates the zone from the set of parameters which have only 1 root from the set of parameters which have 3 roots. So this shape is a cusp like shape. Of course you can keep on refining this and get a pretty much refined shape. In fact, I can do this to show you what I mean. But essentially what I'm trying to say is the cusp shape is something which is a highlight of imperfect bifurcations. There are 3 roots over here, or the 3 fixed points over here, and there is 1 fixed point. Okay, something happens when we transit from a parameter space over here which has only 1 root to over here which has suddenly 3 roots. And now we are more interested in the stability of the roots. So now let us proceed to sort of probe the stability of the roots. So let us go back to our previous okay, so we don't need this really, but With the help of this, I could show you how the output of the Newton solver looks like. The Newton solver is slightly different from the F-solve. In fact, if you double click on Newton, you can have a look at the contextual help of Jupyter Lab. It says func, x naught, f prime, and all these things, and we have simply specified those in the function call. Okay, x naught, f prime, args, and so on. All right, so now let us proceed to find out the bifurcation diagram for different values of H and R. So let me delete these cells. Let me paste this. All right, so now we have to replace this by the Newton solver. Let me copy this line. Let me replace the F solve by the Newton solver. All right, let me replace the function definitions from over here. All right, so we have changed the function definitions, and let me change the looping as well. All right, H. So let us do it for fixed value of H over R. So meaning we are trying to do this X star versus R for various values of H. So we know that when H is 0, we will have the pitchfork bifurcation, something like this. Okay, so now we have to make some more changes. So the strategy is for I in np dot a range. So this line, so let me indent everything. For I in np dot this, if sol1 I is equal to true, and this is from the previous cells that I deleted. Okay, so root is equal to sol0 I, slope at root, so we have to pass H as well if it is greater than 0. Yeah, okay, so let me run this. So let me define H equal to 0.5. Let me start from H equal to 0. Let me not jump the gun. So let me start from H equal to 0 because it's a simple pitchfork bifurcation. Excellent. So this is the diagram of I have to change this as well. This is percentage F, and over here we will print the value of H. Imperfect bifurcation for H equal to this. All right, let me run this again. So for H equal to 0, we have something like this. In fact, let me print only 2 decimal places. Okay, so now let me choose a positive value of H. So we are now probing this entire line, and watch carefully what happens. I mean, if you observe very keenly, we are actually transecting this line, and we are seeing that up until this, so this was R equal to 0, and this is obviously H equal to 0. So up until this point we have only one root, and this entire zone is one root, and over here we have 3 roots. Okay, so up until this point we have one root, and then beyond this we have 3 roots. So this checks out. Now when we increase the value of H over here, we will see that for a long for a larger value of R we will have only one root, and then we will have 3 roots appearing. So let me redo the plot for a higher value of H. In fact, why don't we put all of this inside an interactive function? Let me remove the value of H from this. Let me wrap everything inside an interactive function. So def show H variation with the input will be H. Let us make an interactive widget. All right, let me we have to show the widget as well. Excellent. So when h increases, let us see what happens. Okay, so we see that for a larger value of r, we have only one root, and then we have three roots, out of which the upper branch is still stable. There is a unstable branch and a stable branch. So this is unstable and this is stable. Okay, so this is how the three roots look like. All right, so now when we keep increasing this is how it looks. Okay, same diagram, albeit with a mirror symmetry, it happens for negative values of h. Okay, obviously for this value also will have a similar behavior, but the root behavior will be reflected about the x-axis. Okay, so this is how the roots look like. In fact, we have plotted the stability of the points and all, but there is obviously a much easier way of plotting at least the fixed points. Okay, so what are we drawing actually? We are drawing the fixed points as a function of r for various values of h. And the equation that we're looking at is uh, h plus rx minus x cube. And we have looked in one of the earliest lectures in which we were looking at geometric interpretations of this, and we had made something called as an implicit plot. So we can find out the fixed points using a very simple implicit plot as well. What is the implicit plot? We will draw over this entire domain the isoline or the contour of x dot equal to 0. We will try to find the locus of curves along which x dot will be equal to 0. And those locus should be exactly these points. But just having the locus will not tell us whether uh, that particular isoline corresponds to a stable fixed point or an unstable fixed point. But what we can do is we can later on pass those x and y values of the isoline, check the slope, and then change the color or something. I'm not going to do that now. I'm just going to show you the isolines. Okay, I'm just going to show you how we can make use of the implicit plot. I've not done this for the other plots, but it's really easy to understand. So let me do this. So r1 equal to np dot linspace minus 2 to 2, x1 equal to np dot linspace minus 2 to 2 again. Then we will have r1 comma x1 equal to np dot mesh grid minus 2 comma sorry, this will be x r1 comma x1. Now we will define the function f as h plus r times x1 minus x1 cubed. In fact, this has to be r1. Then we will do plt dot contour r1 comma x1 comma f value. So just to be clear, let us go to the contextual help of contour x, y, z, and what is the extra. So in order to draw certain levels, we can ask the computer to plot for us only a certain level. So over here we will pass levels equal to 0.0, meaning it will plot for us the 0 line. So let me run this. Uh, okay, so all this is outside the function, so we must include them inside the function. Okay, let me run this again. Okay, so let me reduce the number of points we have in the RA so that we can clearly see the overlapping of the two things. So let me just make 20. Okay, so let me run this. Okay, great. So now we can see how the contour lines and the stability and the instability of the points are reflected in a single plot. Okay, so I hope through this little exercise you will be in a position to figure out for any given equation or a vector flow what the fixed points or the contour of the fixed points would look like. Okay, and with the help of the other snippet you will be able to determine whether those points are fixed stable points or fixed unstable points. In fact, by making use of the Newton solver you should be able to find out the shape of the curve without actually using the implicit plots. By using the Newton solver you will have the exact values. By using those exact values and finding out the slope of the vector flow with respect to x, you should be in a position to tell whether that point will be stable or unstable. I've written up a small snippet. Actually, I have basically copied whatever we had done in lecture 9 for the logistic plot, and I have changed all the functional forms. Um, it appears over here. So basically, it's a function which passes r, h, initial condition, and the end time, and we're solving the initial value problem of this particular form, and we're plotting it for various values of r and h. So let me run this. Let's try to okay. So solve underscore IVP we have to import from scipy scipy dot integrate. So from scipy dot integrate import solve IVP. Oops. So there's a question. Okay. Huh. I had written that line. Okay. Anyway. So yeah, after running this, let us see for h equal to 0.24. Let me copy this over here so that we can make sense of whatever is going on. So that we can, oops, we can make sense of whatever is going on. So let h be 0.24. Now let us change r. So let me go from this positive value. Okay, so the fixed point is 1.5. So possibly we need to change the fixed point to the initial condition further. So let me increase this to 2. Alright, let me pass h equal to 0.24 as the default value, and let the default value of r be equal to 2. So let this be also 1.7, so that with this initial condition, default initial condition h and r, we have an asymptotic value of something close to 1.5. Okay, so x is 1.47 something. Good. So now let us reduce the value of r. So as we are reducing the value of r, we should be able to obtain these particular sets of fixed points. Okay, let us see. So x is 1.45, x is 1.41. Let me reduce t end so that we don't have to do so many integrations. Okay, it's slowly decreasing, and at r equal to -2 we should come very close to 0.15 or something. Oops. Okay, it's reducing, it's still positive, and fine. So we do have this monotonous reduction. But now when we start over a value somewhere near to this, so let me change x naught so that for r equal to 2, we end up with this initial condition. Okay, so x naught has to be something close to -2. So let me re-execute this. X naught has to be something close to -2. R has to be something like this. So yeah, okay. So x is minus 1.34 something. So we are over here. Now as the value of r reduces, we will follow this stable branch up until this point. Okay, this is obviously the unstable root. But for this parameter value, this is also a stable point. At this parameter value, that is r equal to something between something close to 0.7. So this is r equal to 0.7. This and this are like two stable points. After this, once we reduce r further, it has to jump from this branch onto this branch and then continue along this branch. Let us see whether that happens or not. So let me reduce t end. Okay, let me reduce r. Okay, so x is reducing, x is still reducing. uh, just a word of caution, in order for this to happen quickly, your computer has to be quite fast, because you're actually solving an IVP every time you change the value of the slider. My computer is a decent computer, it runs reasonably well, can't complain. Okay, 1.23, still negative. There will be a certain point when r is something close to 0.7 where there will be a sudden jump from this stable branch to that stable branch. Okay, we're getting there. R is 0.8, 0.76, 0.75, 0.73, 0.7, 0.69, 0.68, 0.67. Actually, we have to increase the time. There you go. My bad. So it's minus 0.84. R is reducing from 0.9, 0.84, 0.83, 0.78, 0.77, 0.76, 0.75, 0.73. We're still in the negative branch. Boom. From r equal to 0.72, we have the final asymptotic value of 0.98. So we have made a jump from here to here, and this value is actually pretty close to 1. And our mathematics and the intuition that we have obtained from the imperfect bifurcation diagram, everything checks out. So this particular thing is called as so we have essentially what we have jumped between the two stable branches, and we have a catastrophe. Okay, we have catastrophically jumped from one stable branch to another. You can vary the value of h, find out this bifurcation diagram, then plot you can solve the IVP and plot the asymptotic values, and you can check for yourself whether everything works out. Now, a small task, if you will, just try to find out why exactly does the evolution of the IVP look something like this. Look, we are at r equal to 0.72 and h equal to 0.24. Okay, so look, r equal to 0.7. So let's say we plot everything at 0.7. Can we explain why the plot looks the way it does? Let me make h equal to 0.24 and r equal to 0.6. Okay, so we've started. So this is the curve of x dot versus x. Okay, okay, so this is x dot versus x. H is 0.24 and R is something like 0.7, give or take something like this. Now look, we've started, the initial condition is somewhere on this curve. Suppose the initial condition is somewhere over here. In fact, let's see what the actual initial condition was. The actual initial condition was -2. Okay, so the initial condition is -2. Let's do that. So it starts from -2. The initial condition is over here. Let me draw this curve parallelly. So the initial condition somewhere over here. I mean, not over there. The initial condition is somewhere over here. This is x naught equal to -2. So the value of x dot is positive. So the point starts to move towards this, but it moves very slowly initially. So so from this to this, x increases slowly in time. And that explains that, well, is it really something like that? Let us check. It is slowly increasing in time. So there is a very fast behavior like this, but that fast behavior is quickly superseded by a very slow behavior. Actually, that fast behavior also we should be able to explain. Let me go back to the plot and forget about the y limit, and let us rather take a y limit from -4 to 4 perhaps, which is 0.24 and r is 0.7. Okay, so we're starting somewhere over here. So there's a very fast motion and then a slowing down. The slowing down continues up until this point. So this point corresponds to x equal to minus. So there's a slowing down up until this point, and this corresponds to something between somewhere near minus 0.5. So at 0.5, there is a minimum velocity. Okay, after that minimum velocity, the velocity again increases. So once the particle reaches this, there will be a fast motion towards the right, that x will increase, and eventually again there will be a slowing down, and then a fast motion all the way to the fixed point. Okay, so this okay, this point, and then the maxima is somewhere between, the maxima is somewhere near 0.5. Okay, so let us see. Let us see the max, and the equilibrium is near 1. Okay, let's see that. Okay, so x equal to 0 minus 0.2, we started at minus 0.5. We have a change in behavior. So at minus 0.5, we have very slow increase to a fast increase. So a transition from slow to fast. So this is that inflection point in the x versus t curve. After that, we see another change in curve from this fast increase to a slow increase again at x equal to 0.5. So in the xt curve, wherever you see inflection points, be aware that in the x dot versus x curve, you will encounter this kind of local minima or maximum. and it means that you are changing behavior from a positive slope to a negative slope. Okay, so for example, at minus zero point 0.5 you are changing from uh, negative slope to a positive slope, and this is that area of negative slope. So you're increasing time, but x is changing very slowly, and over here you're increasing time, and now x begins to increase rapidly. So that is the changeover in the behavior of x versus t. And over here also, this is increasing in time, this is decreasing in time. So there is a changeover over here, and the changeover corresponds to x equal to 0.5 something around, but it takes a long time for it to reach because of the slowing down of everything. In fact, this particular slowdown is quite large. Can you tell why this slowing down is very large compared to this crossover? It's slowing down and there is a crossover, but over here there is also a crossover, but it's quite rapid. This is quite rapid than this. So the question is why? And the answer is quite straightforward. If you look at this curve, the x dot over here is really close to zero. So the x dot over at this point is going very close to zero, while the x dot over here is something which has a positive value. Okay, so because it comes very close to zero, the velocity of the point on the number line, it becomes very zero, because we are studying the motion of this red particle on the line. And when the velocity itself comes very close to zero, there is a very slow motion towards a positive side. So despite the velocity being positive, it's a very slow, it's a very uh, its magnitude is quite low, and therefore it encounters a very large slowing down, and then the changeover happens. Okay, so this slow dynamics is being captured in the vicinity where you would get 2 points. So this catastrophe happens, and that catastrophe is sort of preceded by that dramatic slowing down, because once we increase the parameter further, we will get rid of that slowing down. It will not happen anymore. Okay, so now when r reduces, okay, when r reduces, that slowing down is slowly lifting up. Okay, so you no longer have that dramatic slowing down. When r is very close, so that this branch comes very close to zero, you will have a very dramatic slowing down. Now when r is increasing, that branch is actually never reached, because this root, okay, this particular point is splitting into two roots. This is one root and this is one root, and it will continuously reach only this root. It will not reach the other root. Okay, so a whole lot of things happen in the bifurcation space. I'm not gonna discuss about the three-dimensional uh, view of this equation. I am, however, going to put a small snippet of how to visualize this in 3D. Okay, so just for completeness, I have put in the small snippet of visualizing the three-dimensional plot in Mayavi. So basically, let me just tell you what I'm trying to plot over here. So if we have uh, R over here, H over here, and the fixed points. So the fixed points should give us some curve in this plane, and there will be zones in which we have only one fixed point, and then there will be three fixed points in a certain zone, and there will be a surface in this x dot RH volume which will correspond to an isosurface which will correspond to a surface in which x dot is 0 all over, and that surface will be the surface of all the fixed points. Okay, that is the meaning of that. So this will be the isosurface of all fixed points, and those three fixed points should also be visible. So let me enlarge this further. Okay, so I've drawn the RH plane in green, and the plane, the isosurface of the fixed point is shown in orange. Okay, So look at how what things are. Here is the cusp. Okay, here is the cusp. If you look closely at this triangle, not triangle, but this thing is the cusp. It mm, it tells you the folding of a sheet of paper. Okay, okay. So well, I cannot really show it with this A4 sheet, but you get the point. Okay, it's a S-shaped curve. This S-shaped curve, and where it starts becoming flat again. So it goes from this S-shaped curve to being flat again, and that entails this cusp over here. Okay, so that cusp is visible in the HR plane. So this is the HR plane, and here there are three roots. Here there is only one root. Okay, there are three roots. One root, one root, one root. Okay, there are three surfaces: the top surface, the middle surface, and the bottom surface. So these things, these overlaps, I've made it transparent so that if you stack multiple transparent layers, you have something which is more opaque. So it helps us in effectively visualizing that there are more layers over here, and more layers correspond to larger number of roots. There's only one root over here. Okay, there's only one root over here. So that cusp is something which we had seen in the HR plane. Okay, so in the 3D zone, the HR plane has that cusp, and we do have that cusp. Great. In the XR plane, so this is the H axis. Okay, this is the H axis. So if we look at this, the fixed points as a function of R for different values of H. Okay, so different transects will give you different values of H, and then you can vary R and see what happens. And the thing is, this inside fold, that is an unstable branch. Okay, these things, this is stable, but this inside fold is unstable. And we are now looking at the HR curve. Let me show the HR curve. We're essentially looking at this across different transects. So H equal to 0.24. It will be somewhere over here. That transect will be somewhere over here. Okay, it's just a matter of how you can visualize whatever is going on. In fact, the H and R are swapped. Let me quickly check this. H and R are swapped. If I'm correct. X level is H. Oh, it is correct. Okay. Anyway, so yeah, I think the H and R axis are swapped. And that swapping happens because of this mesh grid structure. It does not give you something which is that JI stuff, that JI transpose business happens. So let me close this. Let me redo it. Yeah. Okay. So if we look at the X versus R stuff, and we have to look at it at different transects, then you will get that kind of a behavior where you're jumping across different kinds of curves. Okay, so you have to take different transects in this direction to find the iso H lines. And similarly, if you have the time, you can do the plot fixed point versus H for different values of R, for different transects of R, and you will see this kind of S-shaped curve. And that S-shaped curve, as you keep changing R, you will end up with only one root. Okay, so this 3D stuff is visualized not with the help of matplotlib. You can do certain things with matplotlib, but typically in scientific computing you use a data structure called as VTK, and VTK is a data structure which is quite robust, and you can really visualize large data sets. And Mayavi is the name of a module which is available in Python. It has been made by Nthought, and it is a very a robust library to deal with three-dimensional data sets. Another very popular software that deals with BTK files is called as ParaView. You can have a look at that as well. You can export various NumPy arrays of uh, Python to VTK files, which you can then later on visualize using ParaView. And ParaView is also a free open source software. Okay, so with this, we end this particular series of lectures on bifurcations. And next week, we'll start with flows on a circle and two-dimensional flows. So with this, it's goodbye from me. Happy problem solving, and it's goodbye until then.